Okay, so now, ladies and gentlemen, so today we are going to look at Newton's second law. So just a quick reminder from last time, Newton's first law basically said if, okay, if you don't have any net force on an object, so if the total force on the objects are completely balanced, that means nothing is left, then the object will stay at rest or continue at constant motion. So an object at rest to begin with will stay at rest. An object in constant motion will stay in constant motion unless there is a net force. Now, then someone is going to ask, hey, Mr. Newton, so if that's the case, what happens if you do have a net force? Because this rule right here, the first one, only works when there is no net force. So what happens if there is? Okay, then Newton say, haha, we got it covered too. So Newton said, well, I thought about that one too. So what happened when there is a net force? That means what happened when there is a force that is not balanced. So now Newton suggests that, if you have a force that's unbalanced, so for example, you might have a force that's pushing like this way, and that force is, so let's say force number one, which is 100 Newton, and then you have a force that pushes the other way, maybe in this direction, and this force is force 2, and it's so let's say less. So let's say force 2 is 40 Newton. Now then, obviously the forces are not balanced anymore, right? So we cannot say zero net force. So what happens when the forces are not balanced? Well, imagine that it's just two kids or two people pushing a box. The one pushing on the right is as strong as 100, and the one pushing on the left, to the left, is only as strong as 40. Well, then obviously there is a winner and loser in this situation. And the box, if you use your own logic, you will see, hey, then the box should be going like this way, right? It should start moving this way, which is true. But the box wasn't moving to begin with, and it started moving. So what kind of situation is that? It's actually acceleration. So this is actually called acceleration, when you're not moving and suddenly you're moving. So now that means whenever you have a unbalanced force, it will always cause an acceleration. And that's basically what Newton's second law is. An unbalanced force. So an unbalanced force result in acceleration. So an unbalanced force results in an acceleration. So if the forces are not balanced, then whoever wins is going to give you an acceleration. So important to notice is whoever wins. So the acceleration is always the same direction as the winning force. So for example, in this picture, the winning force is the one on the left hand, one to the right hand side. If you can visualize what is 100 Newton and 40 Newton, just imagine this. Let's say every person have the same amount of force, right? So this is like having 100 people pushing to the right and only 40 people pushing to the left. So who wins? Well, the 100 people pushing to the right will win. Therefore, which way will the box go? To the right. Okay, hopefully that makes sense. So if the force to the right, and furthermore, Newton realized two things. Number one is the bigger the force is, the stronger the acceleration, which makes sense. If you have, instead of 100 people pushing to the right, let's say you have 600 people pushing to the right, then you expect the box to go to the right even faster, right? So the bigger the force is, the greater the acceleration. Now, the second thing Newton noticed is it also has something to do with the mass of the box. Now, the mass of the box that you're pushing. For example, if the box is very heavy, imagine that you're pushing a dinosaur, then the acceleration of the dinosaur won't be that great because it's extremely heavy, right? But imagine that you're pushing just a cat on wheels, then the acceleration will be a lot greater with the same amount of people because the cat is a lot less massive than a dinosaur. So therefore, as a formula, Newton's second law equates the two things that the acceleration are related to together. So it says if there's a net force, right? If there's a net force, it will always give you an acceleration based on this equation. F let equals to ma. Now, as you notice in here, in this equation, I have the acceleration of the object related to the mass of the object and the force that's pushing it on. Now, one thing to remember, the acceleration is a vector, so it has direction, and it should be the same direction as the force. So the acceleration and the force should have the same direction. So whoever wins, whichever way wins, for example, in this top version, the 100 Newton to the right-hand side is winning. Therefore, the acceleration should be to the right-hand side. Okay, so let's put that in here. Force, okay, so your net force and acceleration. So net force and acceleration have the same direction. So net force and acceleration have the same direction. Always. Okay, so find out which force wins, and the directions of that is the direction that your object will move and accelerate to. Okay, let's look at units. We know forces are measured in Newton, right? We know forces are measured in Newton. So this is measured in Newton, but mass is measured in kilogram. And acceleration is measured in meter per second square. So technically that means the unit Newton is actually just kilogram multiplied by meter per second square. So Newton, yes, we use Newton's last name to honor him, right? A great scientist who's now not with us. But technically, a force is just kg meter per second square too. So 1 Newton is 1 kg meter per second square. These two units are exactly the same. Okay, so the situation is quite easy. If you know the force or acceleration, you can find, so this equation right here has 3 items, right? 3 things on it. So right now, the way you look at it is if you have 2 out of those 3 things, you can find the third one. Okay, so if you have 2 out of those 3 things, you can find the third one. Now let's see. So for example, a 650 kilogram car accelerates at 4 meters per second, and there is a direction called south. What is the net force acting on it? Well, I have 2 things though. The mass is 650, and the acceleration is 4 meters per second square going south. So now, according to Newton's second law, F let always equals to ma. So this is one of the equations that is on the formula sheet that you will use a lot. Okay, you will use this equation quite a lot. So F let equals to ma, right? Now, F let is, okay, so then if you want the net force, just multiply by mass to the acceleration, so ma, and use a calculator, get the net force from there. So 650 multiplied by 4, which is equal to 2,600 Newton. But we have to have a direction. The acceleration has a direction south, so the force have a direction also south. Okay, so remember, the direction of where you're going is the same as the direction of which way the net force, so the winning force. All right, now sometimes, okay, so let's look at another one. So this one is an easy example. So let's look at another one. Okay, let's look at this one. A box. Okay, this one we'll draw a picture. So a box with 5 kilograms of mass is pushed to the right-hand side. So someone is pushing it to the right-hand side with a force of 10 Newton. Okay, let's put that in. Right-hand side, there is a force. Now I call it a pi force. So if someone is pushing or pulling something, sometimes it's called applied force, like force applied. So Fa. So Fa means applied force. That means someone is pushing. Okay, someone is pushing. Now, why would someone pushing cause a force? Because remember, we talk about this. The skin of your hand has electrons. And the side of the box also have electron. So when you push the side of the box, the skin of your hand repels the skin of the side of the box, and then the box will have a force going to the right-hand side. So it says this force is 10 Newton. So call it 10 Newton. Applied force number 1, 10 Newton. Okay, what else is there? Well, technically, are you on Earth? If you are, we must have gravity. And gravity always points straight down. Again, as you can see in physics, just like last chapter, you will never draw a line without an arrow. Okay, a line is useless. Arrow is useful. Arrow tells you direction. A line tells you nothing. Tells you like magnitude. Now, but remember from last day, what is the supporting force from the ground called? From the electron at the bottom of the box, repelling the electron from the table. That is called a supporting force last day. And remember the name of it is called normal force, right? FN, normal force. Now, so we have normal force, which is always perpendicular to the surface that you're sitting on, which is the table. And we have gravity going down to the middle of the earth. Gravity always exists. Okay. Now, but out of these two, the only one that's new is the applied force in here. And also, you have to remember to use your logic. Okay, for example, in this case, let's say your gravity is approximately, right? Approximately. Let's say your gravity is approximately 50 Newton. Approximately. Now, then what is your normal force? It has to be approximately 50 Newton too. Why? Because you think about it this way. The supporting force is supposed to just counterbalance gravity so that you don't go up and down. Now think about it this way. This is like your cell phone on the table. Okay, your cell phone on the table. You're looking at it from the side. So you have a table, you have your cell phone, you're looking at it from the side, right? Will your cell phone suddenly jump off the table? It won't, right? Will your cell phone suddenly go into the table and then drop to the ground? It won't, right? Have you ever seen things that will just jump off the table unless you have a rocket on it, or maybe there's an engine, or maybe like there's a propeller? You don't, right? So usually when you put things on the table, whatever the mass of the object is, let's say 10 kilogram, and then you have to draw force of gravity, which is approximately, well, not approximately anymore because Fg equal to mg, and gravity on Earth is 9.8. So this will be 98 Newton, right? Now, when you have that, then you think about, okay, what goes on to the other side, which is what is normal force. Well, doesn't the normal force have to be 98 Newton too? Again, why exactly 98? It has to match gravity. Otherwise, your box will fly in the air. You have to match gravity. If the force going up and the force going down is not matching each other, then your box will go up or go down. Again, I'm not saying that boxes can never go up and down, but look at your table. Does it go up in the air all of a sudden? No. Does it go underground all of a sudden? No, right? Usually, things doesn't just move on its own vertically. Now, if I add a force to the right-hand side and no one is balancing it, then yes, I can make the box go to the right-hand side. But up and down, usually for an object that's on the table, up and down is usually balanced. They have to be, otherwise you have flying things just off the table. Look at your pencil. The force of gravity on the pencil goes down. The normal force on the table goes up. And they have to be the same, otherwise your pencil will just jump up and attack you in the face. Therefore, in this picture, we can say, well, I know there's a gravity and I know there's a normal force, but they kind of have to be the same. So they cancel out. Again, if they're not the same, you're going to see flying regular object off the ground. Now, the only other force on this is the applied force. Is there any opponents to that applied force? No, right? No one is pushing to the left, right? So therefore, this is our winner. So if someone asks you, what is the overall force in this picture? What is the net force in this picture? Then you will say, well, the net force, that's the only one thing left. The applied force is my net force, Mr. Chung. Yeah, the applied force is your net force because no one else is left anymore. The gravity is killed by normal force and applied force has no opponent. You don't even have to subtract or add. Now, then what do you do? So you know the applied force is 10 Newton. You can put it on the left-hand side, right? Right-hand side like that. How about your F flat? Now, then you have to use Newton's second law. F net always equal to ma. When you have a net force, it will give you acceleration. So F net always equals to ma. So F flat equals to ma. So you can replace the F flat with ma. Now, mass of the object is 5 kilogram. Acceleration is what you want to find. And 10 Newton is your applied force. Divide both sides by 5, you're done. So 2 meters per second squared. To the right-hand side, I guess. If they do give us a direction, we have to return the direction too. Okay, so to the right-hand side. Easy. Okay. Now, sometimes you might have to mix in a little bit of this with kinematics though. Like sometimes you might have to mix in a little bit of this to kinematics. So look at the next example. A 1,500 kilogram ice cream truck accelerates from rest to a top speed of 45 km per hour in 8 seconds. What is the net force acting on the truck? Now remember, we know that in this kind of situation, the net force is basically just the applied force. But let's get everything in order first. If I want to know the net force and I have the mass, I'll need to know acceleration because F net equals to ma. I will need to know mass and acceleration to get F net. But unfortunately, they give us mass but not acceleration. So we can use F net equal to ma unless we can find acceleration, then we can do this. And well, fortunately, when an object is at rest, the initial velocity is 0. And there's a time of 8 seconds. So we can use that too, 8 seconds. There is a V final, which is your top speed of 45 km per hour. But 45 km per hour is not remotely a good number to use. So 45 km per hour, right? 45 km per hour is not good. We have to change it to meter per second. Divide by 3.6, we change it to meter per second, which is approximately 12.5 meter per second. Okay, so that's your V final. Now, what else can we find? Acceleration. So we want to find this acceleration so that we can do F flat equals to ma. From this, I think the simplest equation we do, V final equal V initial plus AT. So V final is 12.5. V initial is 0. Acceleration is the unknown. And time is 8. So divide both sides by 8. Acceleration is done. About 1.56 seconds. Meter per second square. So meter per second square. Now that's the acceleration. And now we can do net force. So now we can say F flat equals to ma. So F net always equals to ma. And the mass of the box is 1,500 kilogram. The acceleration is 1.56. Multiply together, you get your net force. Okay, so this one is fairly easy after you get your acceleration. About 2,344 Newton. Okay, so F flat done. So we just have to use a tiny bit of kinematics first, get the acceleration so that we can do F flat equals ma. All right, so to very, very quickly finish this off, what if there's more than one force? So far, we have forces that are either canceling out. For example, the Fn and Fg cancels out, so doesn't count. And only one force left, so that is our net force. But what if there are two forces working together? Now, together means they are pointing in the same direction. Now, in that situation, we add them up. Simple as that. So if there are two forces working together, your net force is adding them up. So, for example, Stan and Kyle Aha, Kyle. Stan and Kyle are pushing a 75 kilogram sled along a frictionless ice skating ring. Stan pushes with 55 Newton of force and Kyle pushes with 45 Newton of force. Find the acceleration of the sled. Okay, so you have an object and then you have two people pushing the object. Okay, so there is the Stan, from one force from Stan and one force from Kyle. Now, let's draw a diagram first. I have gravity, again, right? Gravity always exists. Unless you're not on Earth, then you don't have to draw gravity. Otherwise, your first step would be gravity. And then your second step is, are you on a surface? Yes, we are. We are on an ice skating rink. So therefore, there's support on the ground called normal force. Okay, so we have these two. But what do we know about them? They have to cancel out. Otherwise, you have flying hockey puck, right? Hockey puck could fly, but only after you kick it, not just off the ground like that, right? So when you put a car on the ground, it will stay on the ground. Vertically, it won't move. Your car can move horizontally. It can go to the left, go to the right, depending on the engine. But your car usually doesn't just jump off the road on its own and then fly up or submerge underground and become like a submarine. No, it doesn't, right? So these two cancels out. We don't even look at them anymore. So what is actually good to look at is the two forces by. Now, in this question, they never said which way they're pushing. So I'm going to pretend they're pushing from here. They're like two of them. They're standing on top of each other. Okay, forgive me, right? Because I can't draw it like in 3D. So this one. This one is the force from Stan, right? The force from Stan, the applied force from Stan, which is about 55 Newton. And then we have Kyle, which has a slightly weaker, but still significant force that way. This is from Kyle. So Kyle is like, hey, let me help too. Okay, thanks, Kyle. And 45 Newton, right? So now we have Stan and Kyle both pushing in the same direction. All right, so how can we write down our net force equation? So the question is always this, exactly the same. What is the net force in this picture? Okay, we see the up force killing down force. We have two forces to the right and no one to the left. So therefore, imagine that this is a tug of war game. The winner are the forces on the right because you don't have anyone to the left. So that must be the winner. So the net force is the force from Stan plus the force from Kyle. So Kyle force plus Stan force, which in this case happens to be exactly 100 Newton. Right? Because Stan is 55 Newton, Kyle is 45 Newton. Okay, now remember, what can we replace F flat with? F flat always equals to ma. This is Newton's second law. So you always replace net force with ma in the next step. And now divide both sides by the mass of the box. The box is 75 kilogram. So 75 kilogram over here times the acceleration is equal to 100 Newton. So therefore, divide both sides by 100. By 75. Then you get acceleration. So the acceleration works out to be about 1.33 repeating and meter per second square. Now I don't have a direction. I mean, I make up the direction to the right. The question never said anything. Therefore, if the question doesn't have a direction for you, you don't have to force one on your own. Just use whatever they have. So if it's positive, it's positive. If it's negative, it's negative. We're not going to add anything. Okay, easy, right? When two forces are working with each other, you add them. What happens when you have 5 forces working together? You add them. What if you have 16 forces working together? You add them. Just like how you add those vector thing on the test, right? On the kinematic test. So when you have things that are in the same direction, you add them, right? Your bx and cx, add them. Now, but in this case, right, look at it. Your by and cy is done that because they cancel each other, so you don't do anything. It cancels out. Okay, so last thing, right? This is quick. what happened when the forces are not working with each other? Because, I mean, Kyle and Stan doesn't have to be pushing in the same direction. What if they don't agree with each other and they're pushing against each other? They could do that. So, when many forces are acting on the object, some together and some not together, what we need to do is we need to then first add them together and determine which side actually wins. Then all the winners should be added up and subtracted by everyone who is on the losing side. So winners minus losers. Okay, so winner force minus loser forces. That is when they're not working together. Now, remember though, predict which way is the winner by adding all the forces on the same direction and see which side wins. Okay, so example, Batmobile. Okay, you know Mr. Chang's drawings are famously bad, right? I'm not going to be able to draw Batmobile. This is it. Okay. Okay, Batmobile for you. It's technically a rocket, but with wheels on the bottom. But it has an engine. So, now, Batmobile exert a force of, okay, why do they write it like that? It's just 8,500, but in scientific notation, 8,500 Newton force to the east. Okay, so let's get that to the east with a pi force, FA, a pi force of 8,500. This is from the engine, right? From the engine of the car, from the rocket from on the back. It's pushing to the east, right? Okay, and then what else do we have? We have gravity. I mean, yes, the question never mentioned it, but are we on Earth? Yes, then gravity, right? And then are you on the ground? Yes, you are. So there is always supporting force, normal force. Okay. What else can we tell about those two forces right now? Because no one else is going up and down, these two forces must cancel. Otherwise, your Batmobile become bad airplane. It flies. Yeah, it could. It could. I mean, it's possible. Batman does have a vehicle that can fly. I've seen it in the movie, but not this one. This is Batmobile. It's on the car. It's on the ground. Yeah, you can have a force. You can have a normal force greater than gravity. Then, you can fly. Okay. There is another part of this sentence, though. Friction is pulling back on it with a 1,500 Newton. Okay, so first of all, how do we write friction? Now remember, because we have so many forces, they are all F, right? Start with the word F. A pi force, normal force, gravitational force. We use little subscript so that we are not confused. Friction, the subscript is, okay, so force of friction, the subscript is FF, okay, tiny f. So big F, capitalized F, and then tiny f. That's for friction. Okay, so gravity is Fg, right? A pi force is Fa, normal force is Fn, friction is Ff. Okay, so now, which way do we point? Friction pulls it back. Okay, so east is the front, I guess, of the vehicle, so back must be the west. So let's go this way. Friction's here, and it's 1,500 Newton. Okay, so now, please look at this game, this tug of war. Who wins? Look at the FA and the FF. Who wins? Who has a stronger army? Every Newton is one member in your army. Think about it like that. So FA has 8,500 people. Friction has 1,500 people. And when they fight, they just eliminate one after another. So each army send one person up and then they're gone. So at the end, the winner is obvious. In this picture, the winner is FA. What if you have two going to the right and one going to the left? Well, add the two up and see if it's bigger than the other one. So just sum them up. Now, if there's only one thing, then the winner is easy to find. In this case, winner, chicken dinner is our FA. This is the winning direction. Then the losing side is, well, unfortunately, the friction. So let's set up the most important equation for every dynamic question, which is, what is your F let? Now, follow the format above. Winner forces minus losing forces. The winning force is FA. The losing force is friction. So please use Fa minus friction and not the other way around. Okay, so again, Fa is winning, friction is losing. Okay, because Fa is 8,500 people and friction is only 1,500. So subtract 8,500 by 1,500. And then, no, you actually say there is no net force because you're not. We'll talk about friction is actually one of the things that we will talk about either next class or the class after in great detail. If friction is greater than a pi force, in this case, you're not strong enough to move it. You will say net force is 0. So nothing is there. Now, F net always equal to ma. Always equal to ma. So therefore, now you just need the mass of the rocket in order to, oh, there we go. Mass of the rocket is there, 1,250. There we go. The Batmobile is 1,000. Ooh, that's not the color I want. 1,250 kilogram multiplied by acceleration is equal to whatever that's remaining. 7,000 Newton strong. 8,500 going to the right, 1,500 going to the left. The member Q off each other 1 Newton by 1 Newton. So at the end, you have 7,000 Newtons left. Divide both sides by the acceleration, the mass to get acceleration. So the calculations, right, on this chapter on dynamics is generally speaking a lot easier than kinematics. I'm not kidding. The questions are generally a lot shorter too. We're only asking usually 1 or 2 things per question instead of, the question that you do in kinematics, which could ask you up to like 4, 5, 6 things, right? Like, hey, airtime, all of those things. Now, direction. I do think there was a east somewhere. Yes, there was. There you go. So therefore, our winning force point east, our acceleration go east. There we go. Okay, so that is it for this